Hi everyone, today we're going to be talking about the Archimedean property of the real numbers, and our main tool is going to be a property of the real numbers called Dedekind Completeness that is essential to characterizing the real numbers, but a lot of people who haven't taken advanced calculus don't know about it. So I'll explain what Dedekind Completeness is in a moment, but I think I should motivate what we're going to be doing today by actually stating the Archimedean property. So what it says is that the integers are unbounded. Let's precisely state what that means. It means that for all real numbers R, there exists an n in the integers such that n is greater than r. So you can see what this means, that we have the real line here, and no matter how far we go, there's going to be an integer that's above it. So r is here and n is here. That's what we want to prove. It should be a fairly obvious property, but it takes a little bit of effort to prove. So given that, let's get into some definitions. We're going to need these definitions in order to define what Dedekind completeness is, and we're going to use Dedekind completeness to prove the Archimedean property. So the first definition you've probably heard of before. It's the notion of an upper bound, and a lower bound as well. So let S be a subset of the real numbers. Then an upper bound on S is, let's say, we'll call it a U in the reals, such that for all x in S, x is less than or equal to u. And analogously, a lower bound on S is an L in the real numbers, such that for all x in S, x is greater than or equal to L. Okay, so that takes care of an upper bound and a lower bound. We still have a few more definitions to go. 2, a maximum. Well, let's rename our set. So because just because there's an upper bound doesn't mean there's a maximum. So let T be a subset of R with an upper bound. Then a maximum of T is an upper bound that is an element of T. Similarly, if T has a lower bound, and it doesn't necessarily have to have an upper bound this time, then a minimum of T is a lower bound that is an element of T. So you can see the difference between an upper bound and a maximum. A maximum is an upper bound, but it has to be in T. And the difference between a lower bound and a minimum is that the minimum is still a lower bound, but it's also in T. So a maximum is a special form of an upper bound, and a minimum is a special form of a lower bound. Okay, we just have one more definition, and that's the most important one. A supremum of a set that has an upper bound. So if, let's say, it's S or T, the set, and it has an upper bound, is a minimum element of the set of upper bounds. And similarly, I'll give you, let me define an infimum first, and then I'll define for you in a sort of graphical or visual way what these two words mean. An infimum of a set that has a lower bound is a maximum lower bound. So it's the maximum of the set of lower bounds. So let me show you what this means in a more visual way. Let's say we've got a set here on the real line. I'm showing an interval here, but it doesn't have to be an interval. And it has lots of upper bounds. These are all various upper bounds on the set. This is an upper bound, this is an upper bound, this is an upper bound, and so is this one. By supremum, we mean that it is an upper bound, but there is no smaller upper bound. So this is the supremum here. And we have lower bounds here as well. But by infimum, we mean a lower bound such that there is no bigger lower bound. So we can call this I if we want. Although in general in math, I is reserved for the square root of -1. Okay, we've got that done. We've got these definitions out of the way, so let me define for you what Dedekind completeness means. Dedekind completeness of the real numbers states that if a set has an upper bound, then the set has a supremum. And this word supremum, we defined it, but another term for it is least or lowest upper bound. That's why this is called the LUB property as well, this Dedekind completeness. Okay, so with that out of the way, we can finally get settled into proving the Archimedean property. Let me restate for you what the Archimedean property says. It says that for all real numbers R, there exists a natural number, sorry, not a natural, but an integer n. It doesn't have to be natural, such that n is greater than r. Let's prove it. Suppose otherwise. So the negation of this is negation for all r in the reals. There exists n in the integers such that n is greater than r, and that is equivalent to saying there exists a real number r such that for all integers n is less than or equal to r. So this basically says, in human terms, that the integers are bounded above by some real number, r. And clearly that can't be the case, but just like everything else in math, we have to prove it. So let's prove that this is impossible. We need to derive a contradiction because we suppose the negation of what we wanted to prove. So note that we said that the integers are bounded above. So that means the integers by the Dedekind Completeness property have a supremum. Let's call the supremum S. So I'm going to give you the intuition behind the proof first. So let's say we've got the integers going on, and at some point we have an upper bound, call it upper bound U, and that leads to a supremum S. Okay? What we're going to do is look at S minus 1. And S minus 1, well, the fact that S is the supremum means that it is the least upper bound, but that means S minus 1 is not an upper bound, because S minus 1 is less than S, and something strictly less than the least upper bound can't also be an upper bound. So that means there is this integer over here. Let me use a different color. There is this integer over here that is greater than S minus 1. So S minus 1 is less than M. And what we'll do is that we'll take the configuration here, this configuration, and translate it over by 1. And that's going to cause there to be an integer here greater than the least upper bound over here. So let me show you what that means. Now that you have the graphical representation of it, let me show you what it means in terms of rigorous inequalities. So S is the supremum. That implies that S minus 1 is not an upper bound on the integers. So that means there exists an integer M such that S minus 1 is less than M. And then what we get is that S is less than M plus 1. But here's the thing. S is supposed to be the supremum, and M plus 1 is an integer. So that contradicts the fact that the supremum is an upper bound on the integers. So which completes the proof. So let me go back and recap for you what we did. First, I stated the Archimedean property. Then we went through a bunch of definitions, including what an upper bound is, what a lower bound is, what a maximum is, and what a minimum is. Then I defined for you what a supremum is and what an infimum is. This allowed us to define or precisely state Dedekind completeness of the real numbers. And finally, we used Dedekind completeness to prove the Archimedean property, and we did it by contradiction. This contradiction method involved using Dedekind completeness, and if you want to review it, just rewind the video. So thank you for watching, and I'll see you next time.